I briefly want to discuss some aspects of question 1 in the semester test and show you where you need to revise some theory if you are still unsure. If you inspect this rate graph, what you should have realized is that it's an equilibrium reaction because the rate goes to 0 at a point where my conversion is not 100%. So I still have reactants left, but the rate goes to 0. This shows that there is a possibility to have the rate happening in the reverse direction. So this rate has got an opposite sign to that side. It's the reverse reaction kicking in. Of course, this is not going to happen in my reactor if I have adiabatic conditions and I have no change in the molar by an injection of some of my reactants. So we know that it's exothermic because we see an increase in the rate to a maximum. So regardless of the fact that my reactant gets depleted as my conversion is increased, I have the increase in temperature to thank for an increase in the rate before it starts to decline to my equilibrium conversion point. So although this is not the specific ISO rates graph that was used to compile the rate graph that you were given in the test, I want you to keep this in your mind when you think about how the data was generated that's on that graph. So you knew that your inlet temperature was 300 Kelvin and you knew you had adiabatic conversion. So we also know that we have equilibrium at 80%. Between these two, because we have a constant del H reaction, del Cp reaction equal to 0, is the straight line adiabatic energy balance curve. You were not given any information on the temperature on that figure, but what you were given is on the line, as I increase my conversion, the rates were actually given on that figure above. So revise that theory for the adiabatic line to realize that we will always, for an exothermic reaction, have that shape that's shown above, where the rate increases to a maximum and then it decreases until it drops off the cliff here, where we have the equilibrium conversion. The information that was given, however, is that at 70% conversion from a PBR or a PFR, we were given the temperature out of our reactor. So here, you were given an extra point on this adiabatic line. You know the inlet at 300 when X is 0. So using your energy balance and that conversion temperature point that you know at the outlet of the PFR, you are in a position to actually calculate the slope. Maybe not separate information on del H and Cp, but you could calculate those variables as a group. It is important to realize that this 70% conversion temperature that is given cannot be used to calculate the Kc value because that conversion is not the equilibrium conversion. You can, for 70% conversion, after you have determined the del H and Cp, you can actually go and determine what the temperature is when 70% is the equilibrium conversion. And let us just also consider what's going to happen if I increase my inlet temperature. That slope is going to stay exactly the same. At a higher inlet temperature, I am going to go to a lower equilibrium conversion. I will have faster rates. I will have a higher maximum rate, but then I am going to get nowhere faster. You were asked to show the profile of how conversion will change along the volume or the length of a PFR. What I wanted to see is, do you realize that there will be a constant increase in the slope of our exchanges with volume as the rate increases? Then we reach that maximum in the rate at a conversion of 53%. You will have an inflection point and it's going to go to 0 rate. So the slope there is 0. When the conversion is 80%. So it's not going to go wobbly like that. That's just my hand trembling. For that higher temperature inlet, what you must realize is I will have faster rates, so faster slopes of our exchanges with volume, and it's going to go to a lower equilibrium conversion. That inflection point will happen at a lower conversion than in the case where I have the lower inlet temperature. What we must realize is that we can also present this rate graph on a Levenspiel plot. So we will start at zero conversion. The rate is going to increase to a maximum and then it is going to go to zero at that equilibrium conversion of 80%. This maximum occurs around about 53% conversion. So in the question where we had to size the CSTRs in series, your first CSTR, you would like to operate at the point where the rate is absolutely at a maximum so that you can minimize the reactor volume. So that area over there times the inlet molar flow rate will give me the volume of reactor 1. The second reactor, we are bound to go to the desired outlet conversion. We're told that we want 70% conversion. So that area will be used to calculate the volume of my second reactor. I gave some details on a more detailed explanation in the discussion forum on this question. You were asked to calculate the temperature at the inlet of my second reactor. So of course, in order to do that, you needed to do an energy balance up to a conversion of 53%, for which you needed that information from the slope that you had to calculate from the information given on the PFR.